Swayam Prabha. Digital India. Educated India.
Namaskar. So, in the last class we were discussing about the step response of series RLC circuit. So, in this class we will continue our discussion on series RLC circuit, and we will also see the condition when your RLC are connected in parallel and then you provide the step response to that circuit. So, let us recap what we were discussing in the last class. So, in the last class we discussed about the step response of a series RLC circuit, and we discussed that at time t is equal to 0, when the switch is closed, the equation for the particular circuit is L di by dt plus R I plus V is equal to V s, where the V s is the voltage source. Now, when we rearrange, then we got the second order differential equation, and then we discussed that the solution of the equation which we collected based on the mesh analysis of series RLC circuit has two components. One is natural response and another is forced response, and we saw that the total response is the sum of forced response as well as natural response. To get the natural response, we set V s equal to 0 and we found the three conditions like overdamped, critically damped and underdamped situation, and we got the three voltage values under these three conditions. And then we discussed that the forced response is nothing but the steady state value across the capacitor, that is nothing but the voltage V s, and finally we got the three conditions, that is overdamped case, critically damped case and underdamped case. And what we were discussing in the last class is that we have got these three equations in terms of two unknowns, those are A 1 and A 2, which we can, the value of these A 1 and A 2 can be found with the help of seeing the initial and final conditions like initial voltage or voltage across capacitor, initial current through inductor, and similarly the final values, so on. So, what we will do, we will try to understand the fact with the help of one example. So, what we will do, we will take this example. In this example, the switch is opened at time t is equal to 0 and the resistance R, which is given in the figure, is 5 ohm. So, what happens, the switch is initially closed and when it is opened, the circuit is converted into series RLC circuit. So, now let us try to find out the value of current I at any time t and value of voltage at any time t. So, if you see this particular figure, when this switch is initially closed for time t less than 0, what happens, that this particular circuit will give inductor as a short circuit because it is switch is connected for very long period, and the capacitor will be open circuit because it will be charged to certain value and it will act as a open circuit. So, what we left in the circuit is only these two resistances. So, based on these two resistances we can find what will be the value of voltage across capacitor at time t is equal to 0 and what will be the value of current which is flowing through the inductor at time t is equal to 0. So, that would be our starting point. Now, given in the question as a 5 ohm. Now, switch is closed at time t is equal to 0. So, particularly at that time, that is at time t is equal to 0, we need to first find out the value of current flowing through the inductor. So, what we will get, since we can see from the figure that only these two resistances are in the circuit and current flowing through the inductor is nothing but current flowing through the resistances. So, what we get is that 24 volt is the voltage source and value of R is 5, value of 1 ohm resistance is added in series with 5 ohm resistance. So, total resistance of the circuit is 6 ohm and which is applied across 24 volt. So, what we get, the initial current, that is current at time t is equal to 0 is 4 ampere. Now, initial voltage across the capacitor would be same as the voltage across 1 ohm resistor. So, you can see from the figure. So, we need to find out the value of the voltage across the 1 ohm resistor. Since we know that the current which is flowing in the circuit is 4 ampere, which we just calculated. So, the voltage across the capacitor will be 1 ohm multiplied by 4 ampere, that is 4 volt. So, we get the initial voltage across capacitor is nothing but 4 volt. Now, when time t greater than 0, the switch is opened, that means the 1 ohm resistor is now disconnected. So, when you open this switch at time t is equal to 0, this particular resistor will be disconnected from the circuit. Now, in the circuit we will have only R of 5 ohm, 1 Henry inductor and 0.5 farad capacitor. So, we see the typical case of series RLC circuit. Now, in this case what we have to do? We have to first find out the characteristic roots, because it is a series RLC circuit. We discussed what will be the values of the characteristic roots. So, let us find out the value of alpha. Alpha is nothing but R by 2L and we get the value of alpha as 2.5. Omega naught is nothing but 1 by root LC and the value of omega naught is 2. Now, you see that alpha is greater than omega naught, it means that we have the overdamped condition. So, in this case the overdamped means your value of the characteristic roots would be -1 and -4, which you can find from the formula, that is sigma 1 2 is nothing but minus alpha plus minus root of alpha square minus omega naught square. So, since it is a overdamped natural response, the value of voltage across capacitor at any time t can be given as a forced response, that is Vf plus A1 e to the power minus t plus A2 e to the power minus 4t. Now, Vf is the forced or steady state response. So, if you see from the figure, which is the modified circuit when the switch is opened. So, the Vs, the final value, that is value of Vf is nothing but Vs, because when the capacitor is charged to its value, the current will be 0. So, at a steady state the value of Vf would be 24 volt. So, we can now write that Vt is nothing but 24 plus A1 e to the power minus t plus A2 e to the power minus 4t. Now, next task is to find out the value of A1 and A2. Now, from initial condition, that is V at time t is equal to 0, we know that the value of voltage was 4 volt, which we just calculated. So, if we put t is equal to 0 in this equation, we get the 24 plus A1 plus A2. So, finally, we get A1 plus A2 is nothing but equal to minus 20. So, this is what we get from voltage across the capacitor at time t is equal to 0. Next, we know that the current through inductor cannot change abruptly, and it is the same current which flows through at time t is equal to 0 plus, means even when we open the switch, the current across the current through the inductor cannot change abruptly. So, what will be the, since it is the series circuit, So, the current which is flowing through inductor at time t is equal to 0 will continue to flow through the capacitor also. So, we can say I naught is nothing but C dV naught by dt is equal to 4 ampere, which we calculated previously. So, now dV by dt at time t is equal to 0 is nothing but 16. So, this you can calculate from the equation. Now, before using this condition, that is dV by dt at time t is equal to 0, we have to first take the derivative of V. So, we know that this is the value of V at time t. So, let us take the derivative of this. When we take the derivative, we get the value of dV by dt as minus A1 e to the power minus t plus 4 A2 e to the power minus 4t. Now, you will put t is equal to 0. So, you get another equation for A1 and A2, that is minus A1 minus 4 A2 is equal to 16. So, now you have two equations for A1 and A2. First you got from here and second you got from here. So, you can use these two equations and find out the value of A1 and A2. So, when you get the value of A1 at A2, you can put the values in the value for voltage at any time t, and you get the expression for voltage at any time t as shown in the equation. Now, since the inductor and capacitor are in series, the inductor current is the same as the capacitor current. So, what we can say? We can say inductor current I can be given as C dV by dt. So, when you differentiate this and multiply by C, that is the capacitor, you will get the value of current I at any time t also. Now, if you put the value of t as 0, you will get the same expression which we derived for current I at any time at time t is equal to 0, which is our expected result. So, in this way you can calculate the value of unknowns, that is A1 and A2, with the help of initial values, that is inductor current and capacitor voltage. Now, let us move on to the second case, that is step response for a parallel RLC circuit. Now, in this case, suppose the parallel RLC circuit is shown is in this figure. Here what we are doing, we are initially keeping the switch closed at time t is equal to 0, we are opening up the switch, so that we get the parallel RLC circuit. At time t less than 0, the current source will be short circuit. So, when we open it, then it will be converted into parallel RLC circuit. Now, at time t is equal to greater than 0, let us apply KCL at the top node. So, what will happen? The value of current IS would be divided into 3 circuit elements, that is R, L and C. So, what would be the value of current flowing through resistance R, that is V by R. V is nothing but voltage at any time t across the capacitor, plus I, that is the initial, we assume that is the current I which is flowing through the inductor at any time t, plus the capacitor current. Capacitor current can be given as C dV by dt, and the sum of these 3 currents will be equal to the value of source current, that is IS. Now, we know that V is nothing but L di by dt. So, we put the value of V in this equation, and when we rearrange, you will get the final equation as d2I by dt2 plus 1 upon RC di by dt plus I by LC equal to IS upon LC. So, this is what you get from the parallel combination of the circuit. Now, the complete solution will be consisting of natural response as well as forced response. So, you can write the total current I is nothing but forced response and natural response of the current. Now, natural response of the current is same as we got in previous section when we discussed source free parallel RLC circuit. So, we can write those equations. So, what we got, that natural response is nothing but, in case of overdamped, it is A1 e to the power sigma 1 t plus A2 e to the power sigma 2 t, where sigma 1 and sigma 2 are the characteristic roots of the governing equation. And in case of critically damped, the natural response was A1 plus A2 t into e to the power minus alpha t, alpha was the damping coefficient. And in case of underdamped, we got e to the power minus alpha t into A1 cos omega d t plus A2 sin omega t t, where omega d was the damping frequency. Now, these three we got when we discuss about the source free response, that is natural response of the circuit. Now, forced response is the steady state or the final value of I. So, if you see the circuit, when the switch is opened for very long period, this inductor will be short circuit. So, whole current, that is Is, will flow through the inductor, and you can say that the final value of current which is flowing through inductor is same as source current, that is Is. So, you will add the value of Is in place of the Ift, that is the forced response. So, you will get the total value of current It is nothing but Is plus natural response of the circuit in case of overdamped, again Is plus critically damped response of the circuit when source is not available, and plus in case of underdamped we get Is plus the natural response of underdamped circuit. So, these three we get based on the various conditions with respect to your the damping coefficient and the natural frequency of the circuit. So, that is alpha and omega naught. So, under various condition you will get these three values for current It. In case of overdamped, your alpha is greater than omega naught. In case of critically damped, alpha will be equal to omega naught, and in case of underdamped, alpha is less than omega naught. So, now in this particular set of current equations, you know that the A1 and A2 are the two things which are unknown. So, how we can find? We can again use the initial values of current and voltage, that is current flowing through the inductor and voltage across the capacitor, to find out the value of A1 and A2. Now, how we will do? Let us take one example so that the things are more clear. Here, if you see the circuit, the 4 ampere current source is connected across the inductor. So, at time t less than 0, when the switch is opened, the current is flowing only through the inductor. So, you can say that at time t less than 0, the circuit is divided into two parts. So, one part is where the current source is available, second part where voltage source is available. So, at time t less than 0, when the switch is opened, the current will be flowing through the 20 Henry inductor. So, it means that you can simply say current I at time t is equal to 0 is nothing but 4 ampere. This you can get easily from the circuit. Now, you see that the voltage which is connected across the second part of the circuit is 30 U minus T volt. So, what does it mean? It means that at time t less than 0, the value of voltage is 30 volt. At time t greater than 0, this value becomes 0 volt, means when the switch is closed, this voltage source is short circuit. So, this is something which you have to keep in mind, because here the unit step function is u minus t. It means that the value of unit step function is like this, where you have a value at time t is equal to less than t is equal to 0, but it is 0 when t greater than 0. So, with these two things, let us proceed to solve the circuit. For t less than 0, the switch is open. So, we found that the initial current which is flowing through inductor is 4 ampere. Now, u minus t is equal to 30 when t less than 0 and 0 when t greater than 0. So, the voltage source is applied to the circuit only when t less than 0. Now, at t is equal to 0 minus, that means just before the switch is closed, the capacitor acts like a open circuit and voltage across it is the same as the voltage across 20 ohm resistor connected in parallel with it. So, if you see this segment of the circuit, the voltage, because the switch is open for very long period, this will the capacitor will act as an open circuit. So, the voltage across capacitor will be same as the voltage across 20 ohm resistance. Now, at time t less than 0, the value of voltage source is 30 volt and these two are in series because the current will flow through this direction. So, what will be the value of voltage across 20 ohm resistor which is in parallel with capacitor? You can simply use the voltage division and you will come to know that the value of this voltage at time t is equal to 0 is nothing but 15 volt. So, this is our initial voltage across the capacitor when the switch is closed. So, we got two initial conditions, current which is flowing through the inductor at time t is equal to 0 and voltage across capacitor at time t is equal to 0. Now, for time t greater than 0, what will happen? The switch is now closed and we have parallel RLC circuit with a current source. Now, voltage source is off because for time t greater than 0, if you see the circuit for time t greater than 0, this will be 0. So, it means that it will be short circuit. So, now 20 ohm and these 20 ohm both would be in parallel. So, what we can say that the value of effective R which is across the circuit will be 10 ohm because 20 ohm and 20 ohm are in parallel now. This will be short circuited. So, now we have a case of parallel RLC circuit. So, we have inductor, we have capacitor and we will have another equivalent resistance of 10 ohm which is again in parallel. So, what we can do now? We can apply the equations which we got in case of parallel RLC circuit. So, characteristic roots we can simply determine with the help of the values which we calculated previously. So, alpha is nothing but 1 by 2 RC. So, if you put the value of R and C, R is 10, C is 8 millifarad. So, it will become 8 into 10 to the power minus 3 and we get the value of alpha as 6.25. Similarly, the omega naught is nothing but 1 upon root LC. So, if you put the value of omega naught, you get the value of omega naught as 2.5. So, here you will see that alpha is greater than omega naught. That means that this is a case of overdamped circuit. So, what we can say, the value of the roots, that is sigma 1 2 is nothing but minus alpha plus minus root of alpha square minus omega naught square and we get two characteristic roots. So, what we can write now? We can write the value of current IT, that is nothing but equal to the forced response, that is IFT, and here the value of IFT is IS which we just calculated in the case of parallel RLC circuit, and plus the natural response, that is A1 e to the power minus sigma 1 t plus A2 e to the power minus sigma 2 t. So, here IS is equal to 4. This is what we can see from the figure. When the circuit is, the switch is closed for very long period, the capacitor will be acting as a open circuit and the whole current will flow through 20 Henry inductor. So, it means that the Is value is nothing but 4 ampere in the circuit. So, this is what we got, that is 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 equal to 4 ampere. Now, if you put the value of t is equal to 0 in the above equation, you know that I at time t is equal to 0 is 4, which you just calculated. So, you get A2 is equal to minus A1. Now, if you take the derivative of the above equation di by dt, you will get this expression. At time t is equal to 0, di 0 by dt is nothing but minus 11.978 A1 minus 0.521 A2. Now, you know that the voltage which is across the capacitor cannot change abruptly. So, it will remain as 15 volt, and since capacitor is in parallel with inductor, the same voltage will be applied across the inductor also. So, you can simply write the voltage across inductor is nothing but L di by dt at time t is equal to 0. So, this you can use and find out the value of di by dt at time t is equal to 0. So, you got the value as 0.75. Now, you put the value in this equation. So, you get the value of A2. You can use the expression which we calculated when we were putting the value of time t is equal to 0, and we were finding out the equation A1 plus relationship between A1 and A2 when I is equal I is at time t is equal to 0 equal to 4 ampere. So, now we got two equations and we can solve it and we can get the value of A2, and similarly we can get the value of A1. So, now we have A1 and A2, we can simply say the value of current IT is nothing but 4 plus, you can put the value of the expressions, value of the components. So, you get this particular equation. So, this is the final expression of current I in terms of T. So, with this you can calculate the value of A1 and A2 when you have parallel RLC circuit. So, with this we can close our today's session. So, in this session we discussed the step response for series RLC circuit as well as the parallel RLC circuit, and now we will proceed forward to solve these first order second order equations in a more easier format, because in these type of equations till now what we discussed was based on the differential equations. Those were first order and second order differential equations. It is sometimes difficult to solve. So, we will use another technique called Laplace transform, and we will try to understand first the Laplace transform, and then we will apply that technique to solve these first order and second order equations and first order and second order circuits again. Thank you.